Hello world, here's Jorge, and let's continue learning about object detection in PyTorch. In the last video, we defined the variables cell size and number of orientations. Now let's continue moving on, and now we're going to discuss the nn.module and nn.module-dict classes, okay? So let's create here title and discuss about it. Okay, so what is actually nn.module? So nn.module is actually the base class from which all neural networks are going to be inherited in PyTorch. Okay, so we are gonna call it always to be able to use different or to gain access to tools required for defining essentially our network. Okay, so let's write that down. So any custom neural network we create in PyTorch needs to inherit from nn.module. Okay, and this gives access to utilize different functionalities to or on our custom class. Okay. All right. So with nn.module, okay, the layers that we create are going to be automatically managed by PyTorch behind the scenes. Okay. And these layers are going to be defined in our constructor. Our constructor basically is going to be in it. Okay, but let's give an example of how we would utilize nn.module. Okay, let's see. So first of all, we need to import torch, and then we need to import this submodule torch.nn, okay, which basically is going to provide all the building blocks for our neural networks, okay. And actually, there is where nn.module is coming from, right? So import torch.nn as nn, okay. All right. So now let's define our custom nn.module class. Okay. So let's start with that. So let's call it, for instance, simple model. And here we need to call our, say, parent class. Okay, so in this case, it's going to be nn.module. This is the most common choice. Okay, and then is when we define our constructor, and within our constructor, we are going to have all the attributes that we need. That is layers and different variables that as you'll see as we go. Okay, well, here automatically, okay, gives us the structure. And well, here for now, let's not define any variable. Just for this very simple example, we're not going to need that. And essentially, what we are going to do next is, well, what we have obtained automatically from PyTorch, this super line, and what this is doing is essentially initializing the parent class. So it's initializing all or it's allowing us to utilize the different features coming from the parent class NN.dot module. Okay. All right. So now let's define just very simply a layer. Okay, the simplest possible layer. So we are gonna call it here. Let's call it, yeah, just a linear layer. Okay, let's just define a simple linear layer, also known as fully connected. Okay, so let's just call it FC. And let's just define linear. And okay, linear layer, as you can see in the doc string, it takes so input features and it takes output features. Okay, so as input features, just as an example, we're gonna set 10, and as an output features, let's just define 1. Say, okay. Again, this is just a dumb example to understand how we would utilize NN.dot module. Okay. All right. So that is our constructor, just a very simple constructor. And what do we do next? Well, now we are gonna call the forward method. Okay. The forward method is inherited from the NN.dot module too, and essentially what it does is to perform operations or transformations on our input. Okay, so for instance, here we have chosen NN.linear, and NN.linear, if we just search it up, okay, so NN.linear in PyTorch. So what we have is, yeah, you see, it applies a linear transformation to the incoming data. So it applies this linear transformation to whatever our input is. Okay, right now we have just defined it, but in the forward pass, so in the forward method, what is actually happening is applying that operation to the input that we choose. Okay, so let's just define that. So let's call that forward method. Okay, and our input says X. Okay. And that is going to return essentially the computation, so the application of the, in this case, linear transformation into our input. Okay, so simply we're just going to call the actual linear layer on, so basically apply it to the input. All right, and just finally, that is the end of our class. And essentially, we always need to instantiate. And so, our class. Okay. Okay. So in this case, we just have, let's call it model simple. Say, let's call it like that. This is, we're creating an object of our class. Yeah, very simply. So simple model. Like that. Great. And yeah, let's just call it to see how it looks. Great, this is the structure. Okay, just of course very simple. We just have one layer, it's linear. That's all. Okay. Again, some caveats. So for example, here in the super, so in the initialization, I can actually put it here like that. So I can put here initializes the NN.dot module, so the parent class. Okay, so actually here we could explicitly state the base class name. Okay, in this case, NN.dot module. We could do it like that, NN.dot module, and yeah, simply put it like that. Call self here. But again, it's not needed because Python by default understands that the parent class that you're referring to is the one that you encapsulated here in the class. Okay, so there's no need to specify it explicitly here. Okay, great. So what about now? So now the point of this section is actually to compare the nn.module with the nn.module-dect. And what happens with nn.module-dect? Well, actually, let's write it down. So you can think of nn.module-dect as say specialized subclass of nn.module. Okay, so it is actually one specific subclass of nn.module. It's more specific, yeah. Okay, let's make this. Let's mark down this. Great. So why is it useful? Well, is it designed to store PyTorch layers? Okay, PyTorch layers and in a dictionary format. Okay, so we're going to store these layers, utilizing this data structure. And essentially, the key advantage is that it's more flexible. So it's going to allow us to define, or better say, to add layers outside the class. So, for example, nn.module is more rigid. That meaning, if you have defined your class with nn.module, you cannot dynamically, or it's not natural to dynamically modify the class. Okay, so that meaning outside the actual class, you would have to go back to the original class and add or remove the different layers that you. So basically, you will need to go back to your class to customize it. Okay. However, with the nn.module-dect, you can add layers outside the class. Okay, that is the main advantage. So it's more dynamic. So let's actually see an example of that. Okay, yeah. So just for the sake of completeness, let's call here again the import torch. So just here, and again import torch.nn, or import, yeah, as nn. Okay. Now we're gonna define our custom class, or model, so with nn.module-dect this time as the base class. Okay, great. So we do the same. So class, and now we're going to call it simple model-dect, and now we encapsulate it with nn.module-dect. Great. Fantastic. So now we also need to include the constructor. So let's do that. And well, this is the recommended structure for our constructor. Okay. But again, just to make it simple, we're not gonna include modules yet. So let's get rid of this. Okay, and again, we need to incorporate the super line, which is going to essentially initialize our parent class. In this case, is going to be nn.module-dect. Okay, great. And now we are gonna analogously create a linear layer. Okay, and well, difference in syntax here is that as we're dealing with dictionaries, now we need to actually call the key. Okay, so how are we going to call our key? Of course, analogously, fc, and this is going to be equal to nn.linear, and we're just going to set it equal to 10 and 1. Okay, great. Again, we need to define the forward method to apply our say operation, or in this case linear layout, linear transformation, to our input. Okay, so again, forward. Okay, and here we return what? Well, we need to return the operation. So self, and again, this is a dictionary like structure, so hard parenthesis, and we specify fc, apply to x. Okay, great. And again, we can instantiate. Okay, just completely analogously. Essentially, they are the same, right? The same kind of model, but just defined with different, or with respect to different, say, parent classes. But remember, nn.module-dict is actually embedded in nn.module. Okay, it's just a more specific type of class. Okay, but anyways, let's instantiate. Okay, so we have model, and we're going to call it simple dict, say. Great, and we're going to call it simple model dict. Great, and let's have a look at the structure, because our guess is that it should be essentially the same. Indeed, you see, it's exactly the same. It contains the same, of course. It's just that we're utilizing a dictionary here. Okay, great. But let's actually see explicitly, in a practical way, how can we say leverage the fact that this structure is more flexible. Okay, so let's say we want to add another layer. We want to add another layer to our original class. If we were to be utilizing nn.module, we'll have to do that the hard way, in the sense that we would need to define it here. Okay, we will need to hard code it that way. What about with nn.module-dict? Well, we can do it outside the class. Okay, so let's do that. All right. So let's say we want to add a layer called extra fc. Yeah, so what we would do is, okay, let's call the we need to take the object, so model-dict, so model simple, I mean simple dict, right? And here what we need to do is to just call the key, and the key is going to be a new one, of course, because it's a new layer, and we're going to call it extra fc. Okay, great. And this is going to be equal to, say we want to add just a simple linear layer, so nn.linear, and say, for example, just randomly say 1 and 5 here. Okay, well, randomly, watch out with this randomly, because it cannot be random completely. Why? Because the input feature, okay, is going to, it needs to be equal to the output of the first layer. Okay, if they follow one another. Okay, important. Okay, great. So now let's visualize this new addition. Okay, so let's see. Fantastic. You see how automatically, okay, because PyTorch by default is going to append it, okay, just at the end. All right, so you see how it did just that. So, but how about if we wanted to add a layer, but in a specific order. So say we want to add an in-between layer, to this structure. Okay, so how could we do that? Well, first of all, we would need to utilize a specific function. Okay, a specific function that say Python has for us, and it's called ordered dict. Okay, so then we can actually import it. So from collections, import ordered dict. Okay, great. And now let's proceed and insert this extra layer. So let's say, okay, insert our new layer. So in between the previously defined layers. Fantastic. Okay, so let's call this new order. All right, and we're gonna utilize this function. So ordered dict. What happened? Oh, that's strange. Very strange. Ordered dict. Yes. And now, so let's see how it works. So this is a dictionary. Yeah, that's going to remember the insertion order. All right. Okay, so how it works. So we're gonna have actually this structure works as follows. So it takes a list of tuples, all right, and the tuple is confirmed by the key name and the corresponding value. All right, so then how are we going to proceed? Well, remember the first layer is FC. So then in the first, so we're going to have a tuple here, and in the first element of the tuple we're going to have FC, and in the second element of the tuple we're going to have the corresponding value. So in this case, just a model simple dict and the, of course, corresponding key to get the corresponding value. All right, so there we have it. Now what is next? So we need another tuple. So, well, in this second tuple is where we want to add our new layer. Okay, so in the first element we're going to put, okay, so it's going to be let's call it FC in between, say. Okay, and in the second element of the tuple, well, now we don't have it, or it's not defined yet, this extra layer, right, in between extra layer. So we do it explicitly. So we say, okay, linear, and watch out because it cannot be random. Okay, of course it cannot be random, and you want it in between. So we want it in between. Hence, we have input layer. Okay, so we have the FC and the output is 1. Okay, so hence the input here needs to be 1. And the if we go to the next one, the input of the last layer is 1, 2. Okay, so hence we need 1. So just to stress that if your layer is in between FC and extra FC, the output feature of the first layer needs to be equal to the input of the feature of the in-between layer, and the output feature of your in-between layer needs to be equal to the input feature of the last layer. Okay, great. Fantastic. So now we just need to place the last tuple. So in this case, the last one is the extra FC. And in this second position, we're going to have the, so we can, as we already defined this layer, we can call it like that. We can do model, we can take the object directly and say simple dict, and we place here extra-fc here. Okay, fantastic, great. So now, how could we proceed? Well, it's about we actually update our say object, because right now what we did was to add it explicitly, but the object has not been updated. Okay, that's why we couldn't call it here. Okay, so let's do it. So model simple dect, and how do we update it? So just dot updates. Okay, and update with what? With this new order. With this new order that we just defined. Okay, so now how about we call it and see how it looks? Oh, what happened? Something actually unexpected, right? Because look at this. You see, the in-between layer is not actually in between FC and extra FC as we indicated with order dect. Why is it happening? Because actually PyTorch doesn't care about order dect, so it's not going to actually follow this order, and by default is going to append it just the last position. Okay, so what is the trick? How can we actually make it appear in the order, or how can we order our layers as we want? Okay, so the answer is we need to actually define a new object. Okay, so we need to define a new object from scratch, and that will do the trick. Okay, so model simple dect is equal to simple model dect. Okay, simple model dect, just like that. Okay, great. So let's check that out now. Let's see if it worked. Great, it worked. You see, now we have the in-between layer as we wanted to. Okay, fantastic, great. So that's been a clear say introduction to nn.module dect and how it compared to nn.module. Okay, so just to stress that with nn.module dect, we gain say flexibility. We are able to add layers outside the class. Okay, so that's much more dynamic, and mostly when you have a lot of code, right? And you say, okay, I want to add this layer and see what happens, so that you can do it just like in here without having to scroll up and modify it, right? Great. But now let's continue, and now let's talk about gradients. Okay, and for that I have prepared here a small explanation. Okay, so let me take this. Great. Okay, so about the gradient, well, and more specifically in the context of computer vision. Okay, so a gradient, as we know, is a vector. So it's a vector having both magnitude and a direction. Okay, in this case we are dealing with an image of basically a two-dimensional image. Okay, but what is the gradient? What is representing is the rate of change of intensity, okay, in the spatial direction. All right, and again, let's take a 2D image for simplicity. And so what are these elements? So in the 2D image, the first component is going to be the horizontal gradient, okay, or well, basically indicates the change in intensity in the horizontal direction, and we will define that as the U. Okay, and analogously we have the change in intensity in the vertical direction. We're going to call it the V, and it's also known as vertical gradient. Okay, so what are the take notes here? So first of all, we are interested in understanding with how the pixel intensity is going to change. Okay, and more specifically, in what direction is going to change most rapidly. Okay, And why is it useful to use this gradient? Well, it helps us to detect specifically edges. Okay. Why? Because edges correspond to regions where there's a high change in intensity. So we can go from having a very, say, dark pixels, and all of a sudden we go and have white, right? So a really drastic change. This can happen in edges. And that kind of changes we can capture with this kind of gradient. Okay. And also important is to notice that to take the magnitude of a vector, of course, we just need to take the module. Okay, so you just take the square of the values, and we added them up, and take the square root. Fantastic. So okay, that is about say the basic theory about the gradient, of how gradients work in computer vision. And specifically, I highlighted this lecture. I found it very, very interesting and insightful. Definitely recommend. It's in convolutions in image processing. And if we have a look at it, actually, let's do that. Here is brilliantly explained how convolutions work in images. So, for example, here we have a fun image of Mario. And what is actually happening is that these say a square is being passed over the image. Okay, and what is this square really? So this square is actually the kernel, and what it's doing is to actually applying a specific operation that is able to, say, transform a certain square of the original image into say new type of image. Okay, but let's actually see that in action. So let's zoom in, and as you can see here, each kernel position has a number associated to it. That's what we call weight. Okay, and what is going to happen is that this weight value is going to be multiplied by the associated value of the pixel. So in this case, this gray pixel has a number associated to it, and we're going to multiply it by the weight. Yeah, and that is what's going to happen for each pixel. Okay, so for this specific example, what is happening is that the weight is essentially the same. So it's going to be actually the 1/9. Okay, and actually we think about that. That is like taking the average of that specific cell that we are seeing, this blue cell. Okay, why? Because of course we have a 3x3 cell. So if we take actually the common factor out of 1/9, it's like having 9 pixels, and what is happening is that we're gonna add them up. We're gonna add those 9 pixels up, and then we're gonna multiply that resulting addition by 1/9. All right, we're gonna multiply it by 1/9, and actually that is essentially the average. Okay, so that's great. And what actually is observed is that with this kind of operation, what happens is that the result is just the average. The average, of course, of the original cell size. Of course, you see that originally we have some gray, some black, and these say more skin-like color. And of course, we get this as a result, like a mix of quite a bit of dark, quite a bit of black, quite a bit of gray, and just a bit of the skin, right? So we get this color as a result. Makes sense. Great. But what I wanted to highlight here is that basically what is happening is an operation that is applying, basically is transforming our original image, well, in this case just a cell of it, into a new image, and this operation is what we're going to refer to as convolution. Okay, great. Well, now the question is, are we going to apply this kind of convolution in our problem? And the answer is no. Okay, why not? because in our particular problem we don't aim to get a blurry image, because actually what is important to notice here is that as a result of applying this kind of kernel operation, yeah, what we get is a blurry image, as we can actually see right now. Yeah, so that's not what we want for our problem. So we'll have to define a different kind of say filter. All right, but let's actually start say the basic theory down. Yeah, so we are gonna say it's just well, we named this 3.3, so yeah, let's just put 3.0.1. The gradient filter, let's call it like this. Okay. Fantastic. So, okay, so the kernel filter that we are going to use on our input image is going to be, or is going to calculate, better say, the difference in intensity between neighboring pixels. Okay, so actually that's interesting. And why? So what do I mean by that? Well, with neighboring, remember, we are dealing with 2D images. So neighboring could be our left or our right neighbor, or it could also mean our up neighbor and down neighbor, right? So we need to actually specify 2 types of kernel, 2 types of filters. Okay, here. So the horizontal kernel is going to be like, so how are we going to define the horizontal kernel? Well, it is going to be or better say, it's going to take the difference in intensity between the left and right neighboring pixels. Okay, so what we're going to do is take the right pixel and subtract it to the left and divide by 2. And why are we doing that? Well, because that kind of operation is going to capture the change in intensity, which is exactly what we want. We want to identify this change in intensity. And why actually do we want to do that for our original problem? Well, let's think about that. We want to detect edges. Why do we want that? Well, we're dealing with object detection, so clear shapes for our objects, and having a an algorithm that is able to detect these edges is really beneficial for our specific problem. So that's why we choose this kind of operation. Okay. All right. So essentially, we're gonna subtract the right pixel to the left pixel and divide by 2. Great. So what about the vertical? So the vertical, of course, is going to be completely analogous. So vertical kernel. So it is going to be, or it's going to take difference. Well, let's actually write this properly. The difference in intensity between the up and down neighboring pixels. Great. And in this case, we're going to have so down minus up over 2. All right, great. Yeah, that's very clear. But yeah, that's the theory, right? But let's get some. Let's get started with the fun part, say, and actually code it out. So let's call our creating filter D. Okay. So how are we going to specify that we want to take the average? The average. No, sorry, not the average. We want to actually find out the difference in intensity between neighboring, say, pixels. So to do that in PyTorch, we're gonna specify. Well, first of all, we need a tensor, and this tensor is going to have the following shape. Is going to take first of all the left pixel, the middle pixel, the reference pixel, is going to be ignored, hence we place a 0, and the right pixel is going to be taken as well. First of all, well, watch out, because here it needs to be a negative value. All right, now we can actually, as we can see in the doc string, we can actually specify the type. Yeah, again, PyTorch by default is going to work with float 32, right? But just for the sake of completeness, let's actually type it out. So torch float 32. Yeah, great. And of course, don't forget it, we need to divide by 2. Yeah, so there we go. Great. Fantastic. So we just implemented these formula for our weight. Remember, this formula is going to essentially compute the weight associated to our kernel. Okay, so we are hard coding the formula for the computation of the weight associated to our kernel. And I want to stress that this is not common practice. Okay, because what we do is to let our neural network learn by itself, in the sense that it's able to compute the weight by itself. Okay, we don't need to hard compute it. We don't need to define any formula for it to compute it. Okay, but again, as we are taking the shortcut of, say, giving our model again with the analogy of basically a pair of glasses that make it easier for him to essentially detect objects, in this case specifically the edges of the objects. But again, this is not common practice. This is not what essentially is done, say, in big models in practice, right? But anyways, let's continue. And now, just for the sake of it, let's have a look at it. Okay, great. So we have, you see, we're going to take the left pixel and subtract it to the right pixel, and then divide by 2. Okay, great. That's great. And remember, say, just for the sake of curiosity, you see, so say we want to code the weight. The weight associated to the kernel that we saw here previously. Okay, say we want to code this kernel. Okay, so say we want to code the weight associated to this kernel. So in that, if that's the case, we will need to take the average. Okay, so how would our formula change? Well, we would just place here a 1. Okay, because if you think about it, if we just have 1, what we're doing is taking the left one and adding it to the right pixel and dividing by 2. So that is actually taking the average. Okay, so that's not our case, but yeah, just is actually interesting to know. Great. that is very clear now. So let's continue. Let's continue with our, say, definition of HOG. Yeah, and now what we need to do is to actually define the horizontal and vertical gradients. Okay, so we need to define how our, say, gradients are going to be constructed. Okay, and to do that, we actually because what we don't want to do is to hard code everything. So what we don't want to do is to write the code for taking the input, making the computation, that meaning applying the formula to the actual pixels and having a result, having, say, an output out of it, right? We don't want to do that explicitly. We don't want to hard code all that. So what can we do? What we can do is to go to PyTorch and use one of its classes that does exactly that. So does the whole operation for us. And what we're gonna do is to use conv2d of PyTorch. Here we have it. So exactly this is what is happening. So you see the input is the pixel, yeah, the pixel that is multiplied by the corresponding weight, yeah, and then what we can do is actually add a bias to, say, fit say the results to our particular problem. In our case, to keep it simple, we're not going to activate this option. Okay, great. So but we can actually see multiple variables that can be, or multiple arguments that can be placed in a conv2d. Okay, we have in channels, we have out channels, we have kernel size, stride, padding, and so on. Okay, so let's understand what they mean. And to do that, let's actually go back to the CNN website, CNN Explainer, and have a look at it. So in channels, what is this? Well, is it just the number of channels that are actually associated to the input? In this particular example, we have 3. Okay, so input channels will be 3. Okay, then output channels. So actually, it's actually here defined. So you see, so number of channels in the input image, exactly in the CNN website explainer. In that example, is 3. Okay, output channels is the number of channels produced by the convolution. So going back to the CNN website, what is the number of channels produced by the convolution? So you see there are 10 possible object classes as a result of the CNN, so as a result of the whole operation, right? So in our case, these output channels would be 10. Okay, great. So what else? What else do we have here? Well, we see also kernel size, we see stride, we see padding, okay, and many more. Okay, so actually there's a gadget that we can use in the CNN explainer that is actually going to be really useful. Okay, is this one. Great. So actually by default, as you can see, by default we have padding is equal to 0 and stride is equal to 1. So let's just set by default padding equal to 0, and that's great. Okay, so input, we have a cell that is 5 by 5. Okay, great. So, and just for the sake of the example, let's set just the kernel to be a 3 by 3. Yeah, great. So let's see how it works. So essentially, as we saw briefly in the lecture, we saw that the kernel like hovered over the Mario image, right? So here's the same. So here we have how actually it hovers over this cell size, right? Great. But as you can see, actually it doesn't look like it essentially is. Actually it looks like it goes step by step, right? And that's actually determined by stride. So what stride is doing is essentially making the kernel move one by one. So if you actually just focus on this central 3 by 3 cell, right, of the kernel, you see that as I move to the right, you see how it just basically it was just swapped by 1. You see how just moved to 1, yeah. And if I continue moving to the right again, 1, and actually if I move down, it's just going to move 1 down, okay, and so on. But what happens if I set it equal basically to 2, okay? So you see, if you focus on the central cell of the kernel again, you see how now it's not going to move just by 1 step, but it actually does by 2 steps, you see? And same happens if I go down. You see how this central, as I move down, you see I don't have the central of the, well, I don't have the center of the actual kernel here, but I have it down. So indeed, it moved 2 steps down. Okay, perfect. And actually, as you can see, as we increase the stride, okay, it's going to decrease the output size correspondingly. Okay, something to take into account. And the same happens with the kernel. If I keep the other variables constant and I increase the kernel size, the output is going to decrease. Okay, that's something to take into account. Great. So now we understand how stride works. How about padding? Well, let's see what happens now if we increase by 1. Oh, what just happened is, you see, the original input was framed both say in the column and row direction. Okay, and something also very interesting is that our output now didn't reduce. Actually, it was kept constant, and actually that's one of the main benefits of padding our image. That is, that we don't lose information in the sense that the input shape is kept constant. Okay, as we actually see, right? So before applying padding, the output size was a 3 by 3 cell, whilst if we apply padding, it's kept to be 5 5. Okay, and another benefit of using padding is that the edges are captured in a much better way, in the sense that you lose less information by padding your edges. Okay, your entire image. Great. So now we understand how padding, stride, and kernel size say parameters work. And so let's have a look at dilation, right? So dilation, what it's doing is just including some space in between the kernel. And group, what it's doing is actually assigning a number of kernels to the channels. But to actually visualize that better, let's have a look at this actually video. I definitely recommend to understand how particularly compt2d in PyTorch works. But let's actually have a look at the groups section. Okay, let's have a look at there. And what is happening is that, let's say we have an input channel. Let's say we have 3 input channels, RGB. Yeah, and we set our output to be 2, right? So in that case, we're gonna have 2, say, collections of filters of kernels, and y2 because it's determined by the output shape, so the output say result, right? So what's happening is that here by default PyTorch sets groups to be equal to 1. So in that case, what happens is that a kernel is applied individually to each channel, right? And what happens is that as a result, we're going to get an output. So what's happening is, as a result of applying these filter, there is a 3 by 3 by 3 in the sense that one filter is applied. So a filter is applied per channel. As a result, we're going to have output channel of a 2 3 3. Okay, great. But that is in the case of having just one group. That meaning you just have one kernel set. So you have one kernel to be applied to one input channel. Yeah. So what about, let's actually have a look at a more interesting example. Say we have 8 input channels and 4 output channels. Okay, so in that case, what's going to happen is, okay, we have 4 groups. Okay, we're going to have 4 groups because we're going to have 2, 2, 2, and 2. Okay, actually, let's have a look at that. Here, you see, we have 1 group per 2 channels. Okay, that means that we're going to have 4 collections of kernels, and in those 4 collections we're going to have 2 kernels in each collection. Okay, because remember, we need to apply 1 kernel per channel. Yeah, so that's indeed what's happening. We have this collection right there. And something important to notice is, or something important to stress is, that the number of groups, the number of groups that we set, it needs to be a multiple of both the input channel and the output channel. Otherwise, it's not going to work. All right, fantastic. Great. So now we understand how essentially COMP2D works and how the parameters work. Great. So now actually let's proceed and define our horizontal and vertical gradients. Okay. And again, I'm going to stress that we are going to define a gradient, say basically horizontal and vertical gradients, both for actually both for gradient, for grayscale images and RGB. So independently, you'll see. So let's start with that. Well, first of all, let's actually put a header here and say 3.4 conv today. Let's talk about conv today. Great. So essentially, just to stress this PyTorch class performs the convolution operation on a given image for us. Great. Oh, already marked down. Okay. Okay, so horizontal. So let's start with the horizontal gradient for grayscale images. Okay, and we are going to call this, we're going to essentially name this horizontal gradient as du. Yeah, great. So how do we define this? Well, we're going to say du is equal to nn.conv 2d, and well, we just understood how it works. So in channels, remember, is the number of channels that we are going to operate with. Okay, let's start defining the grayscale. So just 1, and as an output, we just expect 1 channel. So just 1 result. Okay. Great. Then the kernel size. The kernel size, actually, I'm gonna set it equal to 1.3, and we'll see why. So kernel size here. And here, I'm going to put the stride. Stride is equal to 1, which, by the way, is by default. We will not need to put it, but anyways, for the sake of clarity, let's do it. And padding, I'm going to set it equal to 0.1, and we'll see why. And the bias, as I mentioned, let's for this practical set it equal to false. Okay, so why the kernel is equal to 1/3, so 1.3, and the padding equal to 0.1. Let's think about that, and let's actually draw it. So imagine we have this cell, yeah, and imagine we are focusing on this specific cell, yeah. So in that case, we would have a kernel based on the specifications that we highlighted. We'll have a kernel like this. Okay, and that would be basically overlapped with a cell like that. Great, fantastic. And why do we want this? Well, remember the definition of our weight computations, or say, yeah, the gradient filter. Yeah, that was take the right pixel and subtract it to the left pixel and divide by 2. Okay, so hence, and take the basically the reference pixel to be ignored. Yeah, so hence what we need is this type of kernel shape to compute, to perform this kind of operation. When we talk about, of course, horizontal, say gradient operation. All right, so it makes sense geometrically to set, say, the kernel size to be 1 row, 3 columns, for the case of the horizontal. Okay, based on the operation. Great. That is in the case that explains why the kernel is 1, 3. So why are we taking the padding to be 0 and 1? And first of all, actually, what is that going to do with, or what is going to, so how is going to, say, modify our original shape, that padding? Well, it's just going to add columns here. Okay, of course the size would be completely proportional to this, but just for the sake of explanation, let's just leave it like that. And so essentially padding is just 0, 1 is adding columns on the sides. Yeah, and that is actually useful when we are taking, where we are focusing on these first, say, cell instead, because in that way we need to have something, at least a reference, on the left. Okay, so that's why we need a padding of 0, 1 when we take, say, when we are scanning in the horizontal direction. Okay, when we're basically applying the horizontal gradient. Okay, so a good question would be, okay, Jorge, so what happens when you add padding in the column? So, or better say, what kind of values does it contain? And the answer is that PyTorch by default, it just adds zeros. Okay, so if we go here and have a look at the come to the documentation, we see that padding mode is set to zeros, that meaning that by default this is, so PyTorch is just going to add zeros for you. Okay, you can change it, of course, based on your problem, but that's what's going to happen by default. Great. And again, because we are dealing with the horizontal gradient, we are going to need to add columns, because our reference is going to be left and right, and same with the, when we reach the right, the top right corner, we're going to have this as a reference. Okay, great. So now that we understand why we need to set our padding to 0, 1, our kernel to 1, 3, let's continue. And now let's do the completely analogous definition, but for the horizontal, so for the vertical gradient. Okay. And you actually can guess now perfectly how it's going to be defined. So this is actually again for grayscale only, and this is vertical. Great. And so how are we going to modify it? Well, first of all, well, input and output channels keeping 1 both. And here, because now we're dealing with the vertical gradient, now what we need is actually to have 3 rows and 1 column. And the padding, now we need it in the, say, top and bottom side. So now we're going to have 1, 0. Great. Great, now we have defined the horizontal and vertical gradients for the grayscale images. But again, we need to do the analogous operation for red, green, and blue channels. Okay, so let's just do that now, and actually it's completely analogous with just some changes. Okay, so now horizontal gradient, and we're going to add here RGB, and this is for RGB images. Great, and here we're going to have just RGB, and here we have, okay, so input channels. For the input channels, we are going to need now to have 3, because we have 3 color channels. And as an output, we are going to get 3 again, okay? So one by one mapping. And for the kernel size, now, well, as we are dealing with the horizontal, yeah, it keeps being the same. The type of kernel is the same because it's the horizontal gradient, okay? And for the padding, same story. So the only things that we need to modify are the input and output channels when we deal with the gradients for the 3D, so the RGB images, okay? So we're gonna have 3 here. We're going to do the analogous for the vertical. So we're going to have 3 input channels, 3 for the output, and again, this is not going to change the kernel size and the padding. Okay, so this is the vertical for the RGB. Great, fantastic. And here, of course, we need to specify that this is RGB. Great. Fantastic. So now we have done that, and what is next? So now what we need to do is to actually hard code our weights, because remember, we're taking the shortcut, and we are not going to let our CNNs to say compute the weights by itself or by themselves. We are going to set the equation that they need to use. Okay, so hard coding weights. Great. So how are we going to do that actually? Well, let's think about it. Remember, we already have a formula for the weights, okay, of our kernels. Okay, so how are we gonna proceed in here, right? Well, remember that the com2d layer computes, so it has intrinsically its own weights computed, okay? But what we want to do is to replace those by the ones that we want to implement, okay? So how can we do that? Well, we can do the following. We can do and we want to access, okay? So we want to access, let's first actually do this. So we want to access the weights on com2d. We want to access and modify them to our, say, will. Yeah. So how do we do that? So we do du, and to access we actually call weight and data. And we could naively think, okay, why not just setting du weight data to just d, right? Because that's what we want to do. We would just want to replace the weight that was intrinsically computed by PyTorch. We're going to replace it by our own, yeah, for our own. Okay, so let's actually think about that. And to actually answer the question of is this correct, we need to actually have a look at the shapes of both, yeah? Because if the shapes are not the same, then that's not going to be correct, right? So actually, let's actually check the shape. Of course, the shape of this is just going to be 3, because we just have, say, a 1D tensor. But what about taking the shape of this? If we take the shape of the U weight data, let's see what happens. Okay, so what we can see is that we have a 4D, and here we have a 1D, so definitely this is not correct as it is right now. So we need to modify this. And how? Well, we just need to reshape. So we need to, so if we go to this so reshape in PyTorch. If we go to torch reshape, so this is basically telling us, look, I'm going to take the same data that you give me, and I'm going to just modify its shape. So the original data is not going to be modified. All what's happening is that the shape is going to be changed. Okay, so hence we're going to reshape our weight tensor. So to do that, let's just apply reshape. And to what shape do we want to do it? Do we want to say change it? Well, we need to change it to the shape of the weights that actually say count is carrying, say by default or naturally. Okay, so that is 1113 in this case. So we simply copy that, which by the way is just input channel, output channel, and kernel size. Yeah, right. Great. And this we want to clone, and why? Because we want to have our essentially we actually don't want our D to be modified. Our original D, we don't want it to be modified by this operation. Okay, so hence we create a copy so that the original D keeps as it is. All right, great. So we essentially have successfully implemented the D, so the say shape, the weight on the DU, gradient. Okay, but now we need to do the same for because remember this is for axis, in this case horizontal gradient, and this is actually grayscale. So grayscale horizontal gradient weights. Okay, so we need to do the same for the rest. So let's now do the vertical. So vertical gradient weights on count to V. So we're gonna do now. Okay, so it's the vertical now, and so what's happening? Well, what do we need to do now? Let's just actually have a look. I mean, of course we can know it right now. Well, let's code it out just for fun. So dv, let's see what shape we'll get. So you see now, because of the kernel, the change for the vertical, of course we got 1131. So all that needs to be changed here is this order in here. Great, fantastic. So now we need to do the analogous for the actual say RGB channels, for the RGB channel. So let's copy paste this. And let's access the now RGB horizontal gradient weights and the RGB vertical gradient weights. Okay, great. So now here we need to of course modify this to be RGB, and same story with this. Great. So now we have that. And okay, so now just let's have a look at the color channels, right? That's right. So let's have a look at this. DU weight data, and now for RGB. Great. So you see now we have 3 because we have 3 color channels, but we're doing U, And again, we're gonna still have 3 because we have also 3 outputs. But you see that the kernel doesn't change with respect to the DU for the grayscale as we expect, because the kernel doesn't, the shape of the kernel doesn't change. Okay. Great. So all we need to do now is to actually, first of all, reshape it. So we need to reshape this to be 3 and 3. The kernel keeps being 1, 3, and now. Well, let's think about this. Let's think about this, because there's actually a better way than doing this. Okay, so we can keep this as it is. We can keep this as it is, and we can actually expand it. We can expand it, because if we expand it, we're gonna get the same result. So we're gonna do expand, and we're gonna do 3. So 3 color channels. And as an output, we are going to have, yeah, so we're going to have a 1. And 1, 3 here. This is basically what we're doing. We're expanding well, let's think about this 1 second. This is dot. Because we want to expand. We want to expand our original, so our grayscale horizontal gradient to be like 3 color channels, right? So the logic tells us, okay, if you want to expand it, well, you're going to need also 3 here, right? Because we want a 3, so we want input and output to be 3 both, as we specified in here, right? We specified in here. So input and output is 3, 3. So this should also be 3, 3. Well, and that's all for the actual horizontal gradient. And what about this vertical one? Well, we just need to do expand and the completely analogous. So we're going to have 3. We're going to have 3. And the rest keeps being the same. So 3, 1. 3, 1 here. Great. Fantastic. So those are our gradients. Those are our gradients. Okay. That's clear now. But now, essentially, we have defined our spatial gradients. Okay. But now we're in a position to start defining our say whole our complete HOG net. Of course, I mean complete, no, I mean just start writing it essentially. So the function, so the class is going to be defined now. So let's start defining it based on what we have, say, developed. So as we specified, we're going to call it HOGNet, and like that. Okay, so now we're going to have class, and we're going to call it HOGNet. And it's going to be nn dot. Remember, here we have two options, either using nn dot module or nn dot module dect. We choose to go for nn dot module dect because we are going to leverage the functionality of or the flexibility of, say, dictionaries. Okay, great. Now let's define the constructor. So constructor, which is going to take as an input. So we're gonna have as say attributes cell size, which we're gonna set equal to 8. Okay, and these number of orientations, and this is going to be equal to 9. Okay, great. That is that starts our constructor. And remember, we need to initialize our parent class. And how did we do that? Well, with the super comment. So write that. Great. And how do we proceed? So now, now remember, we are just defining the gradients. We're defining them, and we're modifying, say, the weights that they embed. Or better say, we are defining them and applying them. But we have not, or we don't want to proceed with the training yet. Okay. Hence, for now, let's turn off the gradients. So turn off the gradients. We're just going to define them, but turning them off without, say, basically using them for now. So for that, we can actually say torch dot very small. Okay, and once here, let's start with the say definitions. So the initializations of our say attributes. Okay, both cell size and number of orientations. So let's start with that. So we're gonna have self number of orientations, which is going to be equal to number of orientation work, of course, because we are initializing it. So orientations, and same story with cell size. Cell size. Great. And just to make it more flexible, not having to write all the time, say, number of orientations or cell size, let's just set so the self number of orientations to be the following. So number of orientations, well, that's actually, because this is, I mean, it actually it also works if we just put number of orientations, but it's more self-explanatory if I put self dot number of orientations. Okay, and same story with CS. So self dot cell size. Great. And now let's proceed with the definition of the spatial gradients. So spatial derivative filters. Great. So well, we can just actually copy paste what we defined above. So we defined the gradient filter, which is going to be this D. Great. So place it down here. Fantastic. So now we have the gradient. Now we want to place the horizontal gradient, and remember, this is going to be a dictionary like structure, so we need to specify it in the following way. We need to do okay, so self, and we need to call the key. It's going to be the U, and now we just can copy paste the horizontal gradient in the for grayscale images. Great. So now we do the same for the DB, completely analogous. Put it like that. DB. Great. And we need to do the same for the color images, so for the 3D channels. So let's do that. Let's do it the same way. The URGB. Great. And completely analogously, we're going to have db RGB. db. Great. Now we need to so implement wait, and this was basically define gradients. Okay, so let's implement it. And how? Well, we can simply actually use the ones that basically are essentially these. Okay, so actually we can copy the whole thing and modify it. So oops. Great. So what we can do here, of course, we need to call it properly. So self du the key. Okay. Dot and the corresponding exactly, and this is going to be db and this is going to be RGB and this is going to be db RGB. Fantastic, great. So that's the basically the whole picture that we have for now. So essentially we have started defining properly HOGNet. But that's been all for this video. I hope it was useful, and I am willing to see you very soon.